I am Radhakrishna, mathematics teacher. Today we are going to discuss the second lecture in quadratic equations and expressions. Yesterday we have discussed some theory points and solved some questions on that. Now we are going to discuss some more theory points about the nature of the roots, then solve the problems. If A, B, C are real and discriminant delta is greater than 0. Yesterday we have discussed what is the discriminant. B square minus 4AC is called discriminant. If A, B, C are real and discriminant is greater than 0, then the roots of ax square plus bx plus c is equal to 0 are real and distinct. We know that roots of this quadratic equation are minus b plus or minus root over b square minus 4ac by 2a, or if you write b square minus 4ac as delta, minus b plus or minus root delta by 2a. Now if a, b, c are real, this is real, this is real. If delta is positive, square root of delta will be a real number. Square root of a positive number is a real number. Then real number plus or minus real number by real number will be real. So the roots are real and they are distinct because delta is greater than 0. For plus sign you will get one root, for minus sign you will get a different root. So this is one point about nature of the roots. Next, second point, if a, b, c are real and delta is equal to 0, then the roots of the equation ax square plus bx plus c are real and equal. If delta is equal to 0, what happens? Minus b by 2a plus or minus 0 means both the roots are same, minus b by 2a, each root is minus b by 2a. So the roots are equal. When the roots are equal, what happens? Suppose each root is alpha, then you can write the quadratic expression as x minus alpha into x minus alpha into a. So it will be a into x minus alpha whole square. So whenever it is said that a quadratic expression is a perfect square, then automatically discriminant is equal to 0. Okay. Next point, if a, b, c are real and delta is less than 0, then the roots of the quadratic equation are non-real complex numbers. Okay. And yesterday we have discussed some basics of complex numbers. Square root of a negative number is called imaginary number, and if x and y are real, x plus iy is called a complex number. Now if you take the roots of the quadratic equation minus b plus or minus root delta by 2a, a and b are positive, real, and delta is negative. When delta is negative, this will be imaginary. Imaginary means some real number into iota. Then if you separate ba, 2a, minus b by 2a plus or minus root delta by 2a, and you can take this as some p, real number by real number is some other real number, plus or minus, this will be root delta will be containing iota. So this is totally in the form of qi or iq. So p plus iq and p plus p minus iq are complex numbers, non-real complex numbers. Why non-real? Because if you take a complex number x plus iy, where I is square root of minus 1, x and y are real. If y is equal to 0, still it is called a complex number. If y is equal to 0, what happens? It is x, real. That means all real numbers are also complex numbers. Okay. That is why I said non-real complex numbers. Okay. And those two non-real complex numbers will be in the form of p plus or minus iq or qi. And these complex numbers which are in the form of p plus iq and p minus iq are called conjugate complex numbers to each other. So, conjugate of 2 plus 3i is 2 minus 3i. Suppose conjugate of 3 minus 3i minus 5, if you want, it is not 3i plus 5. We have to write it as minus 5 plus 3i, then tell the conjugate. Conjugate will be minus 5 minus 3i. Okay. So, whenever the roots are complex, non-real complex numbers, they will be conjugate the complex numbers to each other. They must be in the form of p plus or minus I cube. Means, if you know one root as 2 plus 3i, you can take directly the other root as 2 minus 3i. But condition is when the coefficients are real only. When the coefficients are not real, then even if one root is 2 plus 3i, the other root need not be its conjugate. Okay. Next point, if a, b, c are rational and delta is a perfect square of a rational number, then both the roots of the quadratic equation ax square plus bx plus c is equal to 0 will be rational and distinct. You know the definition of a rational number. If a number can be expressed in the form of integer by integer, p by q, it is called a rational number. Now, take the roots of the equation minus b plus or minus root delta by 2a. If delta is a perfect square, then root delta is a rational number. Then rational number plus or minus rational number means rational divided by rational number. So, finally, the root will be rational. Both the roots will be rational and they will be distinct, because if delta is not equal to 0, they will be distinct. Okay. So, this is the fourth point. Now, coming to fifth point, if a, b, c are rational, when the coefficients are rational and delta is not a perfect square, then if delta is not a perfect square, square root will be remaining there. Then it is called irrational number. If some square root is present in the number, that number is called irrational number. Therefore, the roots are irrational because root delta is irrational. Then if we separate 2a minus b by 2a plus or minus root delta by 2a, and this will be in the form of, this is rational number, rational by rational is rational, p plus or minus, this can be expressed in the form of root q. So, if the roots are irrational, they will be in the form of p plus or minus root q. Okay. And these two irrational numbers, p plus root q and p minus root q, are called surds, and which are conjugate surds to each other. So, conjugate surd of 2 plus root 3 is 2 minus root 3. Suppose it is known that the coefficients are rational and one root is say root 3 minus 2, then you can directly take the other root as not root 3 plus 2, we have to write this as minus 2 plus root 3, then what is the conjugate? Changing the plus sign to minus sign, this will be the conjugate root. So, if one root is known to be root 3 minus 2, you can directly take the other root as minus 2 minus root 3. Okay. This is the property of nature of the roots of a quadratic equation when the discriminant is not a perfect square. Okay. Next, one more point is, if minus b by a and c by a are integers, in the quadratic equation ax square plus bx plus c is equal to 0, we know that minus b by a is sum of the roots, alpha plus beta is equal to minus b by a, and alpha beta is equal to c by a. Okay. When this is sum is integer, and product is integer, then if delta by a square is also is a perfect square of an integer, we know that mod alpha minus beta is equal to root delta by mod a. Squaring on both sides, alpha minus beta is equal to whole square is equal to delta by a square. If delta by a square is a perfect square of an integer, then alpha minus b is an integer. Alpha plus beta is an integer, alpha minus beta is an integer, and alpha beta is an integer. So, obviously, alpha and beta both should be integers. So, this is about nature of roots. Now, after solving some questions, we are going to proceed with the further theory. And during the problems, whenever it is required, I will explain some small concept and give a formula. You should note down in the theory notes separately. First question: if alpha and beta are the roots of x square plus px plus 1 is equal to 0 and gamma and delta are the roots of x square plus qx plus 1 is equal to 0, then what is the value of alpha minus gamma into beta minus gamma into alpha plus delta into beta plus delta? First, let us expand the given product. Alpha minus gamma into beta minus gamma into alpha plus delta into beta plus delta. First, multiply these two and these two separately. If you multiply these two, what will you get? Alpha beta minus gamma into alpha plus beta plus gamma square into multiply these two, alpha beta plus delta into alpha plus beta plus delta square. Now, alpha and beta are the roots of this equation. So, what is alpha plus beta? Sum of the roots minus p, and alpha beta is 1, product of the roots. So, substituting here, what you will get? I will first write gamma square, alpha plus beta is minus p. So, this becomes plus p gamma plus 1. And the second, delta square, and this is this is what? Minus p delta plus 1. Now, what can you do? Gamma and delta are the roots of this equation. Okay. So, gamma satisfies this equation. So, gamma square plus q gamma plus 1 is 0. Okay. Then, what can you do? Gamma square plus q gamma can be substituted as minus 1 here, or this is directly 0. Are you getting 0? Just check minus gamma into this. This is let us multiply this and this and this and this, then it will be convenient because you will get the same kind of signs at both the places. So, I will erase it. Multiply first and third, then you will get alpha square minus you are getting gamma minus delta. The first one is okay. Alpha beta minus of alpha plus beta into gamma plus gamma square into alpha beta plus, I think both are plus, I think. I will check. Alpha plus beta into delta plus delta square. Okay. Now, this is becoming 1 plus p gamma plus gamma square into this is 1 minus p delta plus delta square, and gamma is the root of this equation. So, we got this, then we are getting gamma square plus 1 is equal to minus q gamma. So, I will substitute gamma square plus 1 as minus q gamma, then you will get p gamma minus q gamma. Okay. And similarly, delta is also a root of this equation. So, substituting delta, you will get delta square plus q delta plus 1 is equal to 0. Then delta square plus 1 will be minus q delta. Substitute here, then what you will get? Minus p delta minus q delta. Then take gamma common here, minus delta common here, then you will get minus gamma delta into p minus q into here what you will get? P plus q. What is gamma delta? Gamma delta is product of the roots of the second equation 1. So, this is minus 1 into what is p plus q into p minus q? P square minus q square. So, finally, you are getting q square minus p square. Where is that answer? Option 1 is correct. Let us proceed to second question. Two equations are given, then we want q plus r. If you observe, this equation and this equation are in the same form, just q is replaced by r. So, in place of q or r, if I take x, what will I get? A into 5 plus x square plus 2bx plus c is equal to 0. Now, from the first equation, q satisfies this equation. From the second equation, r satisfies this equation. That means q and r are the roots of this quadratic equation. You write the quadratic equation in proper order, first second degree term, next first degree term, then constant term. Ax square plus 2bx plus 5a plus c is equal to 0. Q and r are roots of this equation. Therefore, what do you want? Q plus r. Q plus r will be sum of the roots of this quadratic equation, that is minus 2b by a. So, answer is first option. Next question. Two students, while solving a quadratic equation in x, one copied the constant term incorrectly and got the roots as 3 and 2. and the other copied the constant term and the coefficient of x square as minus 6 and 1 respectively, then the correct roots are, let us take the quadratic equation as x square plus ax plus b is equal to 0, x square coefficient, 1 minute. Let us take the quadratic equation as ax square plus bx plus c is equal to 0. The first student copied the constant term incorrectly and got the roots 3 and 2. That means he copied the constant term correctly, c is wrong, and got the roots 3 and 2. Which one depends on c? We know that product of the roots is c by a. So here when he got the roots 3 and 2, product of the roots is 6, no? That is wrong. But what is sum of the roots? Sum of the roots is minus b by a. A and b he took correctly. That means sum of the roots must be correct. What is the correct sum of the roots? 3 plus 2, 5. Okay. So we will get b is equal to minus 5a. Now coming to the second student, the other copied the constant term and the coefficient of x square as minus 6 and 1. So the other one took the coefficient of constant term as minus 6, coefficient of x square as 1. So the second student took x square plus bx plus c is minus 6. It must be given copied the constant term and coefficient of x square as minus 6 and 1. Now here when a is 1, what will be the value of b? B will be minus 5. Then you will get x square minus 5x minus 6 is equal to 0. So actually the statement is not clear regarding the second student. The second student copied the constant term and coefficient of x correctly as minus 6 and 1. So the correct value of a is 1, correct value of the constant is minus 6. Then substituting b is equal to minus 5, you will get this equation. What are the roots of this equation? This can be factorized as x plus 1 into x minus 6 is equal to 0. All of you know the factorization. So what are the correct roots? Minus 1 and 6. Minus 1 and 6. So the option D is correct. Next question. If a, b, c are real and distinct, then the roots of the equation b minus c into x square plus c minus a into x plus a minus b is equal to 0 must be real, imaginary, rational, irrational. Here what will you do? To know the nature of the roots, you will apply discriminant. You will find the discriminant. If discriminant is positive, roots are real and distinct. If the discriminant is equal to 0, roots are real and equal. If the discriminant is negative, roots are imaginary. Okay, usually complex roots are called imaginary roots. So you will find out discriminant delta. Delta is equal to c minus a whole square minus 4 into b minus c into a minus b. If it is positive, roots are real. If it is negative, roots are imaginary. Okay. Now, simplifying it, you need to check whether it is positive or negative. That is the method followed by many of you. But you can easily get the correct answer by a very important, a very simple logic. What is that? By observation, you can see that x is equal to 1 satisfies this equation. Putting x is equal to 1, first term is b minus c, second term is c minus a, third term is a minus b, you are getting 0. So, 1 is definitely a root, okay. 1 is what? Real. Now, we have studied that if one root is complex, say 2 plus 3i, then the other root must be its conjugate complex number. That means, if one either both the roots are non-real complex numbers or both the roots are real, only two possibilities. Already we got one real root, x is equal to 1. So, no need to check for the other root must be real, is it not? Or you can say, what is the product of the roots? Product of the roots is c by a means constant term a minus b by b minus c. This is alpha beta. If alpha is 1, beta is this one only. A, B, C are real. So, this is real minus real by real minus real, which is real. Okay. So, directly you can say that roots are real. Okay. If one root is real, the other root cannot be complex because coefficients are all real. And regarding rational, irrational, the real root may be rational or irrational, but that you cannot say. Here one root is one rational, but the other root, this may be irrational. But I said that if one root is in the form of p plus root q, the other root must be p minus root q. Both must be conjugate sides. But when a, b, c are rational, but here it is given that a, b, c are real only. That means here this root can be irrational. Okay. If a, b, c are rational, then definitely this is rational, already one is rational, then c will also be correct answer. But here in this question only a is correct. Next question. If alpha and beta are the real roots of ax square plus bx plus c is equal to 0, where a, b, c are positive and alpha is less than beta, then which are correct? First, it is already given that the roots are real. Given that the roots are real, so no need to check the discriminant. And here a, b, c are positive, then sum of the roots is what? Minus b by a, it is negative, and product of the roots alpha beta is c by a, it is positive. Then what happens when the product of the roots is positive? There are only two possibilities, either both the real roots are positive or both the real roots are negative. Then if you look at the sum of the roots, it is negative. That means both the roots alpha and beta must be negative, because if both the roots are positive, sum should be positive. So we understand that both the roots are negative. So what is the correct answer? Option C. Okay. Next question. If P, Q, R, S are real numbers and PR is equal to 2 into Q plus S, find the minimum number of real roots of the equation. It is given as product of two quadratic equations. So roots of this equation means if this product is 0, either this is 0 or this is 0. So x square plus px plus q is equal to 0, Px plus q is equal to 0 and we get x square plus Rx plus s is equal to 0. Total number of roots of this equation will be 4, because this quadratic equation will have 2 roots, this equation will have 2 roots. Out of 4 roots, what is the minimum number of real roots? We have to find. Now, real roots of this equation depends on discriminant, because coefficients are real, p and q are real, r and s are real. So, it all depends on the discriminant. Let us take the discriminant of the first equation as delta 1. What is it? P square minus 4q, b square minus 4ac. Let delta 2 be the discriminant of the second equation. Delta 2 will be r square minus 4s. There is a relation between p, q, r, s given. Using that relation, we have to know something about the signs of delta 1 and delta 2, then only you will be able to tell the minimum number of real roots. Okay. Now, how can you use this condition? Just observe these two. If you add delta 1 and delta 2, you are going to get q plus s, is it not? Then you can try substituting that condition. So, I will find out delta 1 plus delta 2, p square plus q square, r square you write first, p square plus r square. From the second terms, minus 4 is common. So, minus 4 into q plus s. Okay. Now, let us use that condition. 2 into q plus s is pr. So, this will be minus 2 pr. It will be p square plus r square minus 2 pr. What is it? It is a perfect square, a square plus b square minus 2ab form. You can write it as p minus r whole square. What can you tell about p minus r whole square? It is greater than or equal to 0. If delta 1 plus delta 2 is greater than or equal to 0, what are the possibilities? Either both are positive or one is positive, one is negative. Both cannot be negative, no? Both cannot be negative, is it not? Because if both are negative, sum cannot be greater than or equal to 0. Therefore, at least one of the two deltas must be greater than or equal to 0. Therefore, at least one of delta 1 or delta 2 must be positive. Either both are positive or one is positive, one is negative. Therefore, if both are positive, then this is having real roots, this is having real roots. Total number of real roots will be 4. If one is positive, one is negative, then only one of the two equations will have real roots. So, number of real roots will be 2. So, what is the minimum number of real roots of this product is equal to 0? It is 2. Answer is 2. Okay. Next question. If the roots of the equation a into b minus c into x square plus b into c minus a into x plus c into a minus b is equal to 0 are equal, then a, b, c are in which progression? In this connection, I will just give some basics of AP, GP, HP. AP means arithmetic progression. What is arithmetic progression? If you observe this sequence, in this sequence the difference of consecutive terms is constant. This kind of series is called arithmetic progression or AP. If you take 3 numbers A, B, C in AP, then B minus A will be equal to C minus B, then 2b is equal to a plus c. So, this is the condition if a, b, c are in AP. If a, b, c are in AP, because some of you may not be familiar with the progressions, I am just giving the basics of AP, GP, HP. If A, B, C are in AP, then 2B is equal to A plus C. Now, what is a GP? If the ratio of any two consecutive terms is constant, it is called GP or geometric progression. For example, if you take a sequence 2, 6, 18, 54 and so on, what is the nature of the series? 2 into 3 is 6, 6 into 3 is 18, 18 into 3 is 54 and so on. That means ratio of any two consecutive terms is constant. This kind of series is called geometric progression or GP. Now, 6 by 2 is equal to 18 by 6 is equal to 54 by 18, that is called common ratio of the GP. Now, if A, B, C are in GP, then what is the condition? If A, B, C are in GP, ratio of B and A, that is B by A, should be equal to ratio of C and B, C by B. Then cross multiplying, you will get the condition B square is equal to AC. Similarly, what is HP? If you take reciprocals of the terms of an arithmetic progression, the series is called HP. You take AP first, some 2, 5, 8, 11 and so on. This is AP. If you take reciprocals, 1 by 2, 1 by 5, 1 by 8, 1 by 11 and so on. This series is called harmonic progression or HP. So, if you say A, B, C are in HP, then the reciprocals will be in AP. Reciprocals of AP will be in HP, reciprocals of HP will be in AP. So, we get 1 by A, 1 by B, 1 by C are in AP. Then using this first condition, 2 into middle term, 2 by B is equal to A by A plus C means 1 by A plus 1 by C. If you simplify, you will get B is equal to, taking LCM and simplifying, 2AC by A plus C. If A, B, C are in HP, harmonic progression, then B is equal to 2AC by A plus C. You remember this in further problems, whenever you get AP or GP or HP, directly I will be applying these results. Now, coming to the present question, if the roots of this equation are equal, then A, B, C are in which progression? First, by observation, x is equal to 1 satisfies the equation. If you put x is equal to 1, what you will get? First term is A into B minus C. Next is B into C minus A plus C into A minus B. Putting x is equal to 1. If you multiply inside, AB here minus AB, AC minus AC. In this way, all terms will cancel out, you will get 0. Means x is equal to 1 is a root. But he said that roots are equal. So, second root is also 1. Then take product of the roots. What is alpha beta? C into A minus B by a into b minus c. It should be what? 1 into 1, 1. Then cross multiplying c into a minus b is ca minus cb is equal to a into b minus c. Cross multiplying ab minus ac. Then take AC this side, CB that side, you will get B into A plus C is equal to 2AC. Then B is equal to 2AC by A plus C. What is this property? A, B, C are in harmonic progression. Answer is third option. Next question. If A, B, C are odd integers, show that the equation ax square plus bx plus c is equal to 0 cannot have rational roots. It is a very good question. We can prove it in two ways. Method 1. Let us write the roots of this equation. Minus b plus or minus root over b square minus 4ac by 2a. Given a, b, c are odd integers. Odd integers means they are rational. So, b is rational, a is rational. So, you will get rational roots if b square minus 4ac is a perfect square. Is it not? Here we have to prove that the roots cannot be rational. That means we have to prove that b square minus 4ac cannot be a perfect square. Okay. So, take b square minus 4ac. I am going to prove this with contradiction. Means I will assume that b square minus 4ac is a perfect square. Finally, let us see what happens. If b square minus 4ac is a perfect square, what happens? I will assume it as some m square. Let b square minus 4ac be equal to m square, because it is perfect square. I assumed that it is perfect square. Now, let us see what happens. First, if b square is odd, because b is odd, square of an odd number is odd number. This is odd. What about 4ac? Since 4 is there, it is even. Odd minus even is what? Odd. Odd minus even must be odd. Therefore, this must be odd. If m square is odd, then m must be odd. Is it not? So, here therefore, you understood? Because b square and 4ac are integers, m square is an integer, and m square is an integer and m must be an integer, because it is a perfect square. Perfect square means what? Square of a rational number. If m square is a perfect square and m is a rational number, since m square is integer, m must be an integer and it must be odd integer. So, we get m is odd, m must be odd. Okay. Now, I will write this equation as b square minus m square is equal to 4ac. Now, b is odd integer, m is odd integer. Okay. So, I will take B and M as some 2p plus 1 and 2q plus 1. We can take any odd number as 2p plus 1. Let B be equal to 2p plus 1 and M be equal to 2q plus 1. Any odd number must be in this form. What are P and Q? Integers. P and Q are integers. Now, B square minus M square means 2p plus 1 whole square minus 2q plus 1 whole square is equal to 4ac. What happens if you expand? You will get 4p square plus 4p plus 1 minus of 4q square plus 4q plus 1 is equal to 4ac. Now, cancel 1. In the remaining, 4 can be cancelled on both sides. So, I will get p square plus p here remaining. I can write it as p into p plus 1 minus, what is this after cancellation of 4? Q square plus q. I can write it as q into q plus 1 is equal to, what is remaining in the RHS after cancelling 4? AC. Now, is it possible? We have to check. P is an integer, so p plus 1 is an integer. P and p plus 1 are consecutive integers. Similarly, q and q plus 1 are consecutive integers. And you know that product of two consecutive integers is always even, because one of them must be even, both cannot be odd. Among the two consecutive integers, one must be even. Therefore, this is even, this is even. But what about AC? A and C are both odd integers. So, AC is odd. Now, even number even minus even cannot be odd. Is it not? So, this is impossible. So, b square minus 4ac cannot be a perfect square. It is proved. So, if it cannot be a perfect square, then the roots of the equation cannot be rational. Hence, the roots cannot be rational. Okay? This is method 1. Now, let us take method 2. Method 2 for the same question. The given equation is ax square plus bx plus c is equal to 0. Here also I will go by contradiction. I have to prove that the roots cannot be rational, but I will assume that there is a rational root. If x is equal to p by q is a rational root, then p and q are what? Integers. Then I will substitute p by q, it should be satisfied. So, a into p square by q square plus b into p by q plus C is equal to 0. You can multiply by q square on both sides. You will get AP square plus BPQ plus CQ square is equal to 0. Now, given ABC are odd, what about P and Q? Let us take cases. P and Q are integers. Case 1. Case 1, I will take P and Q both are odd. If P and Q are both odd, then what happens? AP square is odd because A is odd, P is odd. Next, BPQ. B is odd, P is odd, Q is odd. So, BPQ is odd. And what about CQ square? It is also odd. Then AP square plus BPQ plus CQ square, odd plus odd plus odd, can it be 0? Odd plus odd plus odd must be odd, but 0 is even. So, this cannot be equal to 0. So, this case failed. Now, case 2. If P is even and Q is odd, if P is even and Q is odd, what happens? What about AP square? AP square is even because P is even, and second term BPQ. P is even, no? So, BPQ must be even. Third term CQ square. C is odd, Q is odd, so CQ square is odd. Now, if you add them, AP square plus BPQ plus CQ square, can it be equal to 0? Even plus even is even plus odd is odd. So, this sum must be odd. So, it cannot be equal to 0. Okay. Similarly, you take P odd, Q is even, then also same thing will come, not possible. And if both P and Q are even, then you can cancel the common factor 2 and it gets reduced to this case or the next case. So, in every case we fail to prove that the expression is equal to 0. That means P by Q cannot be a root of this equation. Hence, both the roots are, the equation cannot have rational roots. So, this is the second proof. Now, moving to next question. This is a very simple question based on the points we discussed in the nature of roots. If 2 plus root 3 is a root of x square plus ax plus b is equal to 0 and 3i minus 2 is a root of x square plus cx plus d is equal to 0, find the value of ac plus bd. If 2 plus root 3 here it should be given, condition should be given, A and B must be rational, C and D must be real. Those two conditions must be given, otherwise we cannot solve the question. If 2 plus root 3 is a root of this equation and A and B are rational, then 2 minus root 3 will also be a root. So, the other root is 2 minus root 3, its conjugate side. Then what is sum of the roots of that equation? Sum of the roots is minus a is equal to, what is the sum? 4. So, we get a is equal to minus 4. And what is the product of the roots of the first equation? It is b by 1, b. b is equal to, multiply these two. Product of these two is 2 square minus 3, that is 1. Okay. Now, coming to the next, 3i minus 2 is a root of this equation, and it should be given that c and d are real. Then, if 3i minus 2 is a root, the other root is what? Its conjugate complex number. Conjugate complex number is not 3i plus 2. We should write 3i minus 2 as minus 2 plus 3i. Then the other root will be minus 2 minus 3i. Then what is the product of the roots? Sum of the roots? Minus c. Minus c is equal to, what is the sum of these two? Minus 4. So, c is equal to 4. Next, product of the roots, d. d is equal to, if you multiply these two, what you will get? A plus b into a minus b, you will get minus 2 whole square 4 minus 9i square. What is 4 minus 9i square? I square is minus 1. So, this will be 4 plus 9, 13. Product of these two complex roots is 13. So, d must be 13. Now, you want AC plus BD. AC plus BD is equal to A into C minus 16 plus BD 13. So, answer is minus 3. Next question, find the number of quadratic equations which remain unchanged when their roots are squared. That means, even if you square the roots, equation should remain same. Suppose alpha and beta are the roots of one quadratic equation. Even when you square them, quadratic equation remains same, means roots also remain same. By squaring, what you will get? Alpha square, beta square. Quadratic equation with these two roots must be same as quadratic equation with these two roots, means these two roots are same as these two roots. So, what are the possibilities? Alpha square must be equal to alpha and beta square is equal to beta. This is one possibility. Or alpha square may be beta and beta square may be alpha. Alpha square is equal to beta and beta square is equal to alpha. These two are the possibilities. These two are the possibilities. If you take this, you will get alpha into alpha minus 1 is equal to 0 and beta into beta minus 1 is equal to 0. Alpha square minus alpha is 0, means alpha into alpha minus 1 is 0. Here beta into beta minus 1 is 0. Then you will get here, what are the roots? Roots of alpha? 0 or 1. And beta is equal to 0 or 1. Then what is the number of pairs alpha comma beta? 0 0. Next, or 1 1, alpha is 1, beta is 1, or 0 1. I am not taking 1 0 because quadratic equation whose roots are 0 and 1 will be same as quadratic equation with roots 1 and 0. The order is not important. So, we got 3 pairs alpha comma beta. So, there will be 3 quadratic equations. Now, coming to the next case, if we substitute beta is equal to alpha square in the second equation, you will get alpha power 4 is equal to alpha. Then alpha into alpha cube minus 1 is equal to 0. Then we will get alpha into, again factorize alpha cube minus 1, you will get alpha minus 1 into alpha square plus alpha plus 1. Then you will get alpha is equal to 0 or 1, and the roots of alpha square plus alpha plus 1 is equal to 0. I want to discuss some point here. If you take the equation x square plus x plus 1 is equal to 0, if you calculate the roots, you will get minus 1 plus or minus I root 3 by 2. And among them, both are non-real complex numbers, and you can observe that minus 1 plus I root 3 by 2 whole square will be minus 1 minus I root 3 by 2. So, one root is square of the other, and also if this is omega square, because one is square of the other. If you denote minus 1 plus I root 3 by 2 by omega, then omega square will be minus 1 minus I root 3 by 2. And these two are called cube roots of unity, because from this only you got this. So, omega and omega square must satisfy this equation also. That means, if you substitute omega here, omega cube will be 1. Briefly, this is about cube roots of unity, because they are the roots of the equation. If you take x cube is equal to 1, you can factorize if x cube is equal to 1, you will get x minus 1 into x square plus x plus 1 is equal to 0. X is equal to 1 is a real cube root of unity, and the roots of this equation are omega and omega square. So, totally 1 omega square are called cube roots of unity. Okay. Now, coming to this, we got alpha is equal to 0, 1 or omega square. Already 0 and 1 are present here, and here what is beta? If alpha is equal to 0, beta is 0. If alpha is 1, beta is 1. If alpha is omega, beta will be omega square. If alpha is omega square, beta will be omega power 4. But omega cube is 1, so omega power 4 will be equal to omega. Now, 0 comma 0, 1 comma 1 already they are counted here. So, I will remove. And what are the other pairs of alpha comma beta? Alpha comma beta is omega comma omega square or omega square comma omega, but both are same. Order of the roots is not important. So, omega comma omega square is a pair of roots. So, with these two roots we get one quadratic equation. Already we got 3 equations. So, the answer to this question is 4 equations. There are 4 quadratic equations which remain unchanged when their roots are squared. So, answer is 4, right. So, with this we are going to conclude the session for today, and we are going to continue our topic in the next class tomorrow. After solving few more problems, we will discuss theory again and then continue the problems. Okay. Thanks for watching. Have a good day.